Morning, folks. Thank you for this fantastic opportunity to talk something about I'm very, very passionate about, essentially about how generative AI has evolved from its humble origins in statistics to where it is right now, where we are leveraging extraordinarily parallel computing to solve some of the world's hardest problems. So before we go into my talk, I just want to talk a little bit about Intuit, where I lead the AI team here in Bangalore. So in Intuit, our purpose is that we are powering prosperity around the world. So what does it mean? So we basically have a whole bunch of, I do have this thing over here. Yeah, so we have Intuit is essentially the global financial technology platform that powers prosperity for people and a whole bunch of communities. So small businesses, individuals, help manage finances better. The previous speaker was talking about things that they hate doing, filing taxes and so on, very stressful. Intuit has amazing financial products that can help file taxes, especially if you're in the US or Canada. We have amazing suite of products to help small businesses prosper, to make more money better, to basically manage the cash flows better, to basically get new customers. Some of their hardest problems as they focus on doing what they enjoy the most, Intuit powers all of those. If you look at Intuit's strategy, it's essentially an AI-driven expert platform. Intuit is leveraging AI fundamentally to basically power decisions, optimizations for small businesses, millions of small businesses. We essentially have three groups, essentially small businesses, self-employed, and consumers, and we use AI for basically helping all of them. And if you look at the Intuit's AI-driven expert platform, what does it mean? So we have over 10 million small businesses. The company produces almost 65 billion machine learning predictions every day. We have over 2 trillion plus invoices that are managed on our platform per year. This is really on the small business side. On the consumer side, we basically have 90 million customers, 60K financial attributes per customers. That's a scale that we operate in. We have about 810 million, almost a billion AI-driven customer interactions per year that take place on our platform. And we process almost like $106 billion of tax refunds every year. And we have visibility to almost $9.5 trillion of debt that consumers have, and we help them get debt-free, so to help them save more. So those are the things that Intuit does with AI. Now, coming back to the core of the talk, so I'm going to be talking about the evolution of generative AI. So I'm going to start the presentation by quoting a very famous Scottish philosopher. His name is David Hume. David Hume, almost 3 centuries back, he had a prescience to make a wonderful statement. He said that by this means, all knowledge degenerates into probability. This was 300 years back, when people did not even have calculators and so on, an extraordinary visionary. And what exactly did he mean by that? I'll come back to that at the very end of this talk. So I'm going to ask a question for you, for the audience. If I were to give you a data set that looks like this, okay? And now I ask you, can we simulate data similar to these points? Are there any ideas on how would you simulate more points that look like these points? Any thoughts? I'll just give you a problem. I give you this data set, and I say, simulate more data that looks like this. How would you generate one more point which looks like this? Any thoughts? What is it again? Yeah. OK, yeah. You put a density function and you estimate it? OK. OK. I'll basically take away the suspense. So these points were chosen at random from pixels denoting highways in India. So what are all the major highways? You go and pick those points from there, and you randomly select from them, and you end up getting points. So the question that I ask is, could a computer algorithm have learned this from the data itself? At the core of this, answering this question leads us to what generative AI is really all about. So generative AI is essentially probability. It basically learns the probability laws governing data generation from human and natural processes. The probability laws mimic what a human user or context would expect with a reasonable degree of accuracy. So for example, by providing the text of all Sherlock Holmes novels, can an algorithm mimic Conan Doyle's style of writing? By providing pictures of cats with descriptions, can an algorithm simulate a picture of a cat most apt for a new description? By providing a snippet of a song, can we create another new song similar to the provided song? I don't know, you guys there's a Coldplay concert going on, so I don't know how many of you are Coldplay fans, but if you had a snippet of a Coldplay song, how would you basically simulate another Coldplay song? If you can do that, you're basically in the business of generative AI. What is the opposite of generative AI? So we have something called as discriminative AI. Discriminative AI learns to discriminate labels given data. So they learn probability laws that optimize for labeling accuracies for loss functions. So if I were to look at the same problem, by providing excerpts of Sherlock Holmes novels and maybe Hercule Poirot novels, can we have an algorithm that discriminates between the two authors? By providing pictures of cats and dogs, can we have an algorithm say which is a cat or which is a dog? And by providing a snippet of a song, can we detect its genre? So these are all examples of what is called as essentially discriminative AI. For those who are mathematical or math buffs, discriminative AI is essentially the conditional probability of y given x. Generative AI is essentially the probability of x given y. It's just the inverse problem. So for a long time, a lot of machine learning researchers were focusing on a conditional probability that said y given x. We are now coming back and saying that can we do x given y? So what is the x? It could be the picture of a cat. The y is, hey, I want a cat. So that is essentially the mathematical basis of what generative AI really means. Now, what does it take for a machine to learn? I mean, why? We took a lot of effort. We talked about the mathematical basis of how we do this. Now we talk about what are the things that happened that helped really supercharge this field. So what does it take for a machine to learn? So essentially, you need three things. For a machine to learn, it needs to construct a modifiable function that provides an output when it gets feedback. A long time back, a very wise scientist once told me that if you have computer programs that can modify themselves, rather than having a human create those computer programs, you're in the business of machine learning. So if you look at think of the simplest machine learning algorithm that you can think of, logistic regression. I'm pretty sure a lot of you know about logistic regression. It's essentially, if you look at it, it's basically a simple rule. But then, can the program modify the rule by itself? You come back and say, if x is greater than 10, you basically say yes. If it is less than 10, you say no. So, but this greater than 10 and less than 10 was coded by human beings. Is there a way for us to basically come back and have these functions modify themselves? So when you basically have algorithms that can modify themselves with feedback, you essentially start doing machine learning. So to enable that, you need a loss function that can be computed. Very important. If without a loss function, you cannot do machine learning. So one of the first things that I asked myself is what is your objective function? Can you mathematically formulate it? If you can do that, you can do machine learning. Second part is that how do you optimize a loss function? By modifying the function. So that's the second part of it. And the third part of it is essentially you need a representative data set for feedback and optimizations. Now, early ML researchers, long time back, were very constrained by the types of functions that lend themselves to optimization. They came back and said, hey, I can only do linear regression. I can only do sigmoid functions with logistic regressions. And they were coming back and saying that, hey, can we get exact solutions for solving linear regression? So if you want to do linear regression, there's actually an entire theory that's called the Gauss-Markov theory that exists over there that says that there are exact solutions for basically estimating linear regression. People focused a lot on that. And then they also looked at very simple families of loss functions, mean squared error, cost entropy loss. All of these loss functions lend themselves to the mathematics of how we optimize them. What changed, was auto-differentiation and gradient descent algorithms on GPUs that basically helped researchers completely move away from saying, let's define simple functions for solving these problems. So if you look at what are the three things that have happened, the first is gradient descent. The foundations of the gradient descent algorithm that powers a lot of generative AI actually was published in a very seminal paper sometime in the 1970s by Larry Aramayo that talks about how can we minimize functions which just have continuous derivatives. To be very precise, it's called Lipschitz continuity. How do you basically optimize functions that are Lipschitz continuous functions? Basically, you come back and say that if you have a function that you can only compute derivatives for, can you minimize it? 1970s, the mathematical basis for the gradient descent algorithm was actually in this paper. This actually comes back and proves that gradient descent algorithms will actually end up under like reasonable assumptions, actually end up converging to the optimum. The question, though, is that will this optimum be guaranteed? So if you look at a lot of the things over there, if you have like let's say fine-tuning an LLM right now, okay, it's going to take a long time to converge. The reason why it's taking a long time to converge is that it's very hard to prove optimality of convergence for a lot of gradient descent algorithms. The second main innovation that happened after that was auto-differentiation. Can we compute exact derivatives of arbitrarily complex functions? So if I were to basically say, I'll give you a function, and then you want to compute its derivative. So what would you do? You do numerical derivations. Right? You'll just do f of x plus h minus f of x divided by h. That's how you compute numerical derivatives. Problem with that is that it's an approximation. Right? And then there are approximation errors that will keep going on if it becomes like a very complex function. Auto-differentiation solves that problem. So what does auto-differentiation do? You can compose primitive functions with known higher-order derivatives, and then you use that to differentiate exactly without loss of precision. It does not suffer from numerical errors, and most importantly, you have a DAG. That's a directed acyclical graph that is over there. So for example, if you basically want to differentiate a complex function like x1 times x2 plus sine of x, you can actually differentiate that exactly using auto-differentiation. Auto-differentiation was a key development that took place, interestingly, by a bunch of researchers in Brazil sometime in 2003 who figured out how they could do this exactly. And the last part of it is essentially stochastic approximations. How do we basically compute these derivatives over very large data sets? And then Monte Carlo simulations basically help with that. What Monte Carlo simulations enabled is that you can parallelize the computation of these derivatives over thousands and millions of cores on GPUs. That's the reason why NVIDIA is so powerful. The technology that they have enables a parallelization of the computation of these derivatives at scale using Monte Carlo simulations. That is essentially why we can learn extraordinarily complex functions at scale using compute technology that we have. So those are the main three foundations of what generative AI is all about. Essentially about how do you have gradient descent algorithms, you basically have auto-differentiation, and then you have parallelizable computation of derivatives at scale that has enabled a lot of the developments that you're seeing today. What does it take for a machine to learn human language? Very interestingly, human language is essentially a sequence of tokens. Okay, so when you realize this, you basically made a fundamental discovery. So a language model essentially assigns probability to sentences or sequence of words. So for example, machine translation, probability of high winds tonight is greater than probability of large winds tonight. Spelling and grammar, the office is about 15 minutes. There's a spelling mistake. That is going to be lesser than the probability of having the correct spelling. So for every sequence, for every sentence that is there that you can think of in human language, you basically have a probability. That is exactly what a large language model does. It assigns probabilities to sequences of words. You have text generation. You have a whole bunch of things that you can do with that. And yeah, so what is a large language model? You basically want to compute the probability of a sequence or a sentence of words. The related task, if you formulate this as a probability problem, you can come back and say, generate the next word that's going to come in from a sequence of words. You can even say that if there's a missing word that is going to be there somewhere in a sequence of words, how do you basically impute that? All of these become possible. So conditional probability enables prompt engineering. So at the core of all large language models, you have a probabilistic model that essentially computes probabilities to sequence of words. And if you look at the evolution of generative AI, finally, is that initially it came back and said that you want to train a model from scratch. I used to remember when I started my career, people used to come back and say, give me the data set, I want to train the model from scratch. A lot of fun I had. And then it slowly moved towards pre-tuning and fine-tuning models. And then after that, we now have a situation what is called as in-context learning, where you basically can provide a lot of the information that is needed for the LLM to perform its task as data as an input itself. And finally, where it's evolving right now is essentially multimodal AI, where you have context that's coming in not just from text, but from videos and audios and a whole bunch of things. So you have more general purpose models with less training for specific tasks. So this has, in essence, been how models have been evolving. So I promised, why did I start with that statement by David Hume? So David Hume, this is an excerpt from his treatise on experimental method of reasoning. He made the statement, By this means, all knowledge degenerates into probability. And this probability is greater or less according to our experience of the veracity or decidefulness of our understanding, and according to the simplicity or intricacy of the question. This was David Hume's 300 years ago, who basically summarized the essence of all human knowledge, which is all human knowledge degenerates into probability, and that is exactly what LLMs are doing right now. So thank you so much for your time.